Everyday events move naturally in one direction, downwards. But chemical reactions appear to operate in two directions. Under one set of conditions, reactions move forward. Under another set of conditions, the reaction appears to stop. And given the right circumstances, reactions can reverse, products can dissociate, and raw materials climb back on the shelf. Even harder to swallow, chemists would have us believe that both forward and reverse reactions happen at the same time. As colorless dinitrogen tetroxide is warmed, it begins to dissociate into reddish-brown nitrogen dioxide. And if nitrogen dioxide is cooled, it reacts to form colorless dinitrogen tetroxide. Left alone to reach the same temperature and pressure, the reaction appears to stop with a mixture of both nitrogen dioxide and dinitrogen tetroxide in each flask. But chemists would like us to believe that the reaction has not stopped. Instead, millions of reactions operate in one direction to balance out millions operating in the other. A condition they call dynamic equilibrium. If this is so, we need a model that explains how the individual molecules are behaving. Let's combine 1 mole of colorless hydrogen gas and 1 mole of purple iodine gas in a 1-liter flask. Heat it to 445 degrees Celsius. The purple color begins to fade, indicating that iodine is being consumed. Eventually, the gas becomes almost colorless and remains so. Balancing the equation, we would expect the reaction to produce 2 moles of hydrogen iodide. On analysis, however, the flask actually contains only 1.6 moles of hydrogen iodide, 0.2 moles of hydrogen, and 0.2 moles of iodine. Has this reaction actually stopped? Or has it reached dynamic equilibrium with ongoing reactions in two directions? Let's look at a collision model based on the kinetic molecular theory. The kinetic molecular theory proposes that molecules are in constant motion. So every individual molecule undergoes endless collisions. The energy of this motion is bound up in several forms, such as rotation, vibration caused by the movement of atoms within the molecule, and translational or straight-line motion through space. As heat is applied to any molecule, the heat energy is transferred into kinetic energy. Now let's consider how two molecules might meet and react. If they lack enough energy, they simply bounce off each other. With more energy, but the wrong angle of attack, they do the same. But with sufficient energy, at the right angle, they react. Hydrogen and iodine form hydrogen iodide. Of course, two hydrogen iodide molecules may also meet. With sufficient energy, at the right angle, they will also react to form hydrogen and iodine. If heat energy can be converted to kinetic energy in individual molecules, this allows hydrogen and iodine a downhill energy slide to form hydrogen iodide. But heat also boosts the hydrogen iodide's kinetic energy and allows it a downhill reaction to reform hydrogen and iodine. And in a mess of molecules, there's no reason why both reactions should not go on at the same time. Now, just how does this model explain dynamic equilibrium? Initially, if there is only hydrogen in iodine, only this reaction can possibly take place. The quantities of hydrogen and iodine drop quickly. Naturally, at the same time, the quantity of hydrogen iodide increases rapidly. But as the concentration of hydrogen iodide builds, this reaction speeds up. As fewer and fewer hydrogen and iodine molecules remain to react, this reaction slows down. Finally, the rates of both reactions match. As time goes on, the system reaches a stage where the quantity of hydrogen and iodine remain constant, and there's no further gain in hydrogen iodide. Equilibrium has been reached. It's a dynamic equilibrium because the reaction may be as vigorous as before, but there is no net change in the concentration of any of the participants. So it merely looks stopped. The forward rate of the reaction equals the reverse rate. This model of chemical reactions forces us to change the way we look at chemistry. If reactions do eventually stop, then this one-way symbol appropriately describes chemical reactions. But if reactions are dynamic, even when they appear stopped, it takes the formation of only a few product molecules to raise the possibility of a reverse reaction. If this is the case, whenever we see this sign, we must mentally see double. Of course, since we can't actually see the molecular activity to prove our model valid, it would be nice to have some experimental evidence of dynamic equilibrium. Let's take a container of hydrogen and iodine at a fixed temperature and pressure and allow it to reach equilibrium. When the reaction appears to stop, we have a mixture of three gases. Carefully separate them and measure the amount of each. Now take a second container under exactly the same temperature and pressure and the same amount of each gas, but with one change. We will use a radioactive isotope of iodine. Since we have already determined that these are the amounts and conditions of equilibrium, no reaction should take place if equilibrium is truly a stop in the reaction. A week later, we should be able to separate out the reactants and find them unchanged. Is this what really happens? Almost. The amounts of the ingredients have not changed, but there is now a significant amount of radioactive iodine combined in the hydrogen iodide. Clear evidence that equilibrium is dynamic. There is a forward and a reverse reaction, continually exchanging atoms from molecule to molecule.